Hi everyone. In this video, I am going to discuss about example of root locus. This is the previous examination question, JNTUA Anantapur previous examination question in the year April 2021 R15 regulation. The example in this year, the open loop transfer function of a unity feedback control system is given by g of s is equal k into s plus 9 by s into s square plus 4s plus 11. Sketch the root locus of the system. And this is the example of root locus. So now coming to the solution, given that the open loop transfer function g of s is equal k into s plus 9 divided by s into s square plus 4s plus 11. This is the given open loop transfer function. First calculate the poles and zeros. The poles of open loop transfer function as the roots of this equation, and the denominator term is the characteristic equation. So calculate the poles, and one pole is at s is equal to 0 and s square plus 4s plus 11 is the characteristic equation. The roots of s square plus 4s plus 11 is equal to 0 roots are, so using the expression using ax square plus bx plus c is equal to 0 is the characteristic equation. The characteristic roots of ax square plus bx plus c roots are minus b plus or minus square root of b square minus 4ac divided by 2. So this is the standard expression. So using this equation, now here we want to calculate the characteristic roots of the denominator polynomial. One root is at s is equal to 0, one pole is at s is equal to 0, and another poles of s square plus 4s plus 11 roots. S is equal, now here the b value minus 4 plus or minus square root of minus 4 square minus 4 AC. A value is 1 and C value is 11 divided by 2A. 2 into A value is 1. So that implies S is equal minus 4 plus or minus square root of, so minus 4 square 16 minus 4 into 1 into 44 11, 4 into 1 into 11 44 divided by 2, so which is equal minus 4 plus or minus square root of 44 minus 16 minus 44 minus 28 divided by 2, which is equal to, so minus 1 is written as j square, square root of j square is j, minus 4 plus or minus j square root of 28 divided by 2. S is equal minus 4 plus or minus j square root of 28 is 5.29 divided by 2, so that is equal minus 2 plus or minus j 5.29 divided by 2 2.64 2.64. Now here the roots are complex conjugate roots. So therefore the roots of denominator polynomial are poles of given open loop transfer function. Therefore the poles of open loop transfer function at s is equal to 0 is the one pole, and second pole is at s is equal to -2 plus j 2.64, and third pole is at s is equal to -2 minus j 2.64, and the total number of poles of the given open loop transfer function, the total number of poles given transfer function small n is equal to 3 poles. Next, calculate the zeros of the open loop transfer function. And zeros of the transfer function at s is equal to -9. S is equal to -9. That is the one pole. The zeros of given open loop transfer function g of s are only at s is equal to -9. Only one zero. So therefore the total number of zeros small m is equal to 1. So that is step 1, to locate poles and zeros, to determine poles and zeros. Step 1. In ordinary graph sheet, locate poles and zeros. And this is the ordinary graph sheet to sigma plus j omega. X-axis is the real part of s, that is sigma, and y-axis is the imaginary part of s. S is equal to sigma plus j omega. Sigma is the real part and j omega is the imaginary part. And after that, represent scale, and this is the origin point. One unit is equal to 1, and this is 1 unit, and this is the negative real axis, and this is the positive real axis. -1, -2, -3, -4, -5, -6, -7, -8, -9, -10, like that up to -50. And this is positive real axis, +1, +2, +3, +4, like that up to infinity. And imaginary axis, and this is positive imaginary axis, and this is the negative imaginary axis. And positive imaginary axis, the scale is plus j1 plus j2 plus j3 plus j4 plus j5, like that. And negative imaginary axis, minus j1 minus j2 minus j3 minus J4, minus J5, minus J6, like that up to minus infinity. And after that, locate the poles and zeros in this graph sheet. So from the given open loop transfer function, only one zero, that zero is at s is equal to minus 9. The zeros are represented by small circle. Zeros are represented by small circle, and poles are represented by small cross mark. So now here, what are the zeros? The zeros at s is equal to minus 9. So zeros are represented by small circle, and this is the 0. S is equal to minus 9. And what are the poles here? The poles are at s is equal to 0 and s is equal to minus 2 plus or minus j 2.64. The poles are represented by small cross mark, and this is one pole at s is equal to 0, one pole, and the second pole is s is equal to minus 2 plus j 2.64, and this is the minus 2 plus j 2.64. This is plus j 2.64, j 2.5, j 2.6, approximately minus 2 plus j 2.64, and this is the second pole. And third pole is minus 2 minus j 6.24, approximately, and this is the third pole. Okay, poles and zeros are represented in ordinary graph sheet. And second step, determine root locus branches. To determine root locus on the real axis. So the root locus on the real axis can be determined. Now here on the real axis, this is the real axis. On the real axis, one pole and one zero is there. One pole and one zero is there. So now consider the test point between s is equal to 0 pole and s is equal to minus 9 pole. Consider a small test point between s is equal to 0 pole and s is equal to minus 9, 0. So now here I am considering this is the test point. My pen mark is the test point. So now here I am considering this is the test point. To the right of this test point, count the total number of poles and zeros. And what is the right side of the test point? And this is the right side of the test point. To the right of this test point, okay. So this is my test point. This is my test point. To the right of this test point, count the total number of poles and zeros. So only one pole. That one is the odd number. That one is the odd number. So between s is equal to 0 pole and s is equal to minus 9 is a part of the root locus. Once again, I will explain the same point. Find out the root locus on the real axis. So now here on the real axis, only one pole and one zeros are there. Now I am considering the test point between s is equal to 0 pole and s is equal to minus 9, 0. Suppose for example I am considering the test point between s is equal to 0 pole and s is equal to minus 9, 0. This is my test point. To the right of this test point, so this is the right side of this test point. To the right of this test point, count the total number of poles and zeros. Here, to the right of this test point, only one pole. That one is an odd number. That one is an odd number. So, between s is equal to 0 pole and s is equal to minus 9, 0 is a part of the root locus. Highlight the root locus. Highlight the root locus branch. root locus. Root locus branch. And similarly, next consider the test point to the left of s is equal to minus 9, 0. And this is s is equal to minus 9, 0. S is equal to minus 9, 0. Consider the test point to the left of s is equal to minus 9, 0. And this is the my test point. To the right of this test point, count the total number of poles and zeros. To the right of this test point, the total number of poles and zeros are 2. 1 pole and 1 zero. The total number of poles and zeros are 2. So, which is an even number? Which is an even number. So, to the left of s is equal to minus 9, 0 is not a part of the root locus. S is equal to minus 9. To the left of s is equal to minus 9, 0 is not a part of the root locus branch. Next, step number 3 to determine angles of asymptotes and centroid. So we know that the expression of angles of asymptote is plus or minus 180 degrees into 2q plus 1 by n minus m, where q is equal to 0, 1, 2, 3 and so on, n minus m minus 1. Here, from the given open loop transfer function, where small n is the total number of poles and small m is the total number of zeros. So given open loop transfer function, the total number of poles are 3 and the total number of zeros are 1. So that is small n is equal to 3 and small m is equal to 1. So first calculate the ranges of the Q. So Q is equal n is equal to 3, m is equal to 1. 3 minus 1, 2, 2 minus 1, 1. So therefore Q is equal to 0, 1. So in this equation, substitute Q is equal to 0 and Q is equal to 1. Calculate angles of asymptote. First substitute if q is equal to 0, if q is equal to 0, then angles of asymptote is equal plus or minus 180 degrees into q is equal to 0, 0 minus 1, plus or minus 180 degrees by 3 minus 1, 3 minus 1, 2. So that is equal plus or minus 90 degrees. And next q value is if q is equal to 1, in this equation substitute q is equal to 1, the angle of asymptote is equal plus or minus 180 degrees into 2 plus 1, 3 divided by 2, 290s, 90 into 3, 270 degrees. So plus or minus 270 degrees. And what is the total angle? Plus or minus 360 degrees. So plus or minus 270 degrees is also written as, is also represented as minus or plus 90 degrees. In anti-clockwise direction, plus 270 degrees, while or in clockwise direction, minus 90 degrees. So plus or minus 270 degrees or minus or plus 90 degrees. So these are the angles of asymptotes. Next, calculate the centroid. So we know that the basic expression of centroid C is equal sum of poles minus sum of zeros divided by n minus m. Now here what are the poles? The poles are at s is equal to 0 and s is equal to minus 2 plus or minus 2.64, and zeros are at s is equal to minus 9. And sum of poles 0, minus 2 plus j 2.64, and another pole is minus 2 minus j 2.64, sum of poles minus sum of zeros. So what are the zeros? Only here s is equal to minus 9 divided by n minus m. N is equal to 3, m is equal to 1. So plus j 2.64 minus j 2.64 is cancelled. Minus 2 minus 2 minus 4, minus into minus plus 9, minus 4 plus 9 plus 5 divided by 3 minus 1, 2. 5 divided by 2, 2.5. So the centroid value is 2.5. So mark the centroid on the graph sheet and mark the angles of asymptote in an ordinary graph sheet. So now here the centroid is 2.5. Centroid is 2.5. So 2.5 is on positive real axis. Positive real axis. Highlight the centroid. And this is 2, this is 3, and this is 2.5. And this is the centroid. This is the centroid, and centroid is the center point. Centroid is the center point. Measure angles of asymptotes. So now here, what are the angles of asymptotes? If q is equal to 0 plus or minus 90 degrees, and if q is equal to 1, plus or minus 270 degrees, or minus or plus 90 degrees. Centroid is the center point. Measure angles of asymptote using protractor. So plus 90 degrees, and this is plus 90 degrees. If q is equal to 0, indicate dashed lines. And if Q is equal to 1, the angle of asymptote is plus 270 degrees, measure plus 270 degrees using protractor, or minus 90 degrees, and this is minus 90 degrees. This is minus 90 degrees, angles of asymptotes. Angles of asymptotes. Step number 4, to determine breakaway and break-in points from the location of poles and zeros and from the knowledge of the typical sketches of the root locus, it can be concluded that there is no possibility of breakaway point or break-in point. And this is the typical sketches of the root locus. The typical sketches of the root locus. So from this root locus graph, from the location of poles and zeros and from the knowledge of typical sketches of the root locus, it can be concluded that there is no possibility of breakaway point or break-in point. So that is step number 4. Next, step number 5. Step number 5. To find the angle of departure. Step number 5. To determine angle of departure and angle of arrival. The angle of departure and angle of arrival. When we calculate angle of departure and angle of arrival, the angle of departure and the angle of arrival can be calculated at the complex conjugate open loop poles and complex conjugate open loop zeros. So given open loop transfer function లో complex conjugate poles ఉన్నాయంటే we can determine angle of departure, and from the given open loop transfer function complex conjugate zeros ఉన్నాయంటే we can determine angle of arrival. So now here in this example, so given open loop transfer function, only complex poles are there. So what are the complex poles? At s is equal to minus 2 plus or minus j 2.6. So complex poles అనేవి availability ఉన్నాయి కాబట్టి now here we can determine angle of departure. The angles of departure can be calculated at complex conjugate open loop poles. So given transfer function లో complex poles అనేవి availabilities ఉన్నాయి కాబట్టి now here we can determine angle of departure. And this is the Laplace transform plane. S is equal to sigma. Sigma is the real part of S, and S is equal to j omega. J omega is the real part of S. Now here, what are the poles? One pole is at S is equal to 0, and another pole is at S is equal to minus 2 plus j 2.64, and another pole is at S is equal to minus 2 minus j 2.64, and 0 is at S is equal to 0. So these are the poles and zeros in the ordinary graph sheet. Okay, now here we want to calculate the angle of departure. So the procedure of angle of departure is, and this is one complex pole and this is another complex pole. So this complex pole is considered as a point A, and this complex pole is considered as a complex conjugate, A conjugate. So draw the line from this complex pole A to remaining poles and zeros. So draw the lines from this point A to remaining poles and zeros. And what are the remaining poles? This is another pole and this is another pole. And what are another zeros? This is another zero. So draw the line from this pole and this zero. And this is one pole. This is another complex pole. And this is pole at 0. So draw the line from this complex pole to the remaining poles and zeros. And this angle is considered as theta 1. This angle is considered as theta 1. And this angle is considered as theta 2. And this angle is considered as theta 3. And what is this value? And this is minus 2. And this is minus 2. And this is minus 9. And now here what is the value? This is J 2.64. And this is minus J 2.64. And in this angle, this is the opposite side and this is the adjacent side. And here to here the distance is 2.64 and here to here the distance is minus 2.64 and this is minus 2. So first calculate the angle theta 1. So here, so from this figure, the angle theta 1 is equal and this total angle is 180 degrees. This angle is 180 degrees. So theta 1 is equal 180 degrees minus tan inverse of opposite side. And what is the opposite side? 2.64 divided by adjacent side. And what is the adjacent side? 2 divided by 2. So in your calculator, first set in degree mode. Set in degree mode. And after that 180 degrees minus shift tan inverse of 2.64 divided by 2 is 1.32. Tan inverse of 1.32. So we get 127.14 degrees, the angle theta 1. And angle theta 2, angle from this figure, the angle theta 2 is equal 90 degrees. Angle theta 2 is equal 90 degrees. And angle theta 3 is equal, this angle theta 3 is equal tan inverse of opposite. And what is opposite side? 2.64 divided by adjacent side. And here to here, what is the distance? 7. Tan inverse of shift tan inverse of 2.64 divided by 7, 20.66 degrees. 20.66 degrees. So these are the angles theta 1, theta 2 and theta 3 from this figure. And the expression of and the basic expression of angle of departure at a complex pole A is equal 180 degrees minus sum of angles of vectors to the complex pole A from other poles plus sum of angles of vectors to the complex pole A from other zeros. So now here we can determine angle of departure at a complex pole A. This complex pole A to other poles, from other poles. What are the other poles? And this is another pole and this is another pole. Sum of angles of vectors to the complex pole A from other poles. So that is theta 1 plus theta 2. 180 degrees, theta 1 plus theta 2. Once again, sum of angles of vectors to the complex pole A from other poles. Now here what are other poles? This is another pole and this is another pole. So what is the sum of angles of vectors? Theta 1 plus theta 2 plus sum of angles of vectors to the complex pole A from other zeros. Now here what are other zeros, and this is another 0. So that angle is theta 3. So now here substitute theta 1, theta 2 and theta 3 values. 180 degrees minus theta 1 value is 127.14 plus theta 2 is 90 degrees plus theta 3 is 20.66 degrees. So the 180 minus 127.14 plus 90 degrees plus 20.66, which is equal to minus 16.44 degrees. So at complex pole A, the angle of departure is minus 16.44. So next similarly calculate the angle of departure at complex pole A conjugate. Similarly calculate angle of departure at pole A conjugate. Angle of departure at pole A conjugate is equal minus of angle of departure at pole A. So what is the angle of departure at pole A? Minus 16.44 degrees minus of minus 16.44 degrees minus into minus plus, which is equal to 16.4. Next step number 6 is to determine crossing point of imaginary axis. So to find the crossing point of the imaginary axis, first calculate the characteristic equation of the closed loop system. So given that open loop transfer function is there, so first calculate the closed loop transfer function. We know that the transfer function of the closed loop system is C of S by R of S is equal G of S by 1 plus G of S into H of S. Now here the unity feedback system, the feedback element H of S is equal to 1. That is equal. So given that, what is the open loop transfer function? K into S plus 9 by S into S square plus 4S plus 11 divided by 1 plus K into S plus 9 divided by S into S square plus 4S plus 11. In the denominator and numerator, take the LCM, and after LCM, simplifying the RHS term of the above equation, we get the equation, the transfer function of the closed loop system is K into S plus 9 divided by S into S square plus 4S plus 11 plus K into S plus 9. So this is the closed loop transfer function. In this closed loop transfer function, the characteristic equation is denominator polynomial is the characteristic equation of the closed loop system. So this is the denominator polynomial. This denominator polynomial is called as characteristic equation of the system. So that is S into S square plus 4S plus 11 plus K into S plus 9 is equal to 0 is the characteristic equation of the system. So that is equal S cube plus 4S square plus 11S plus Ks plus 9K is equal to 0. The procedure of crossing point of imaginary axis. In this characteristic equation, substitute S is equal to J omega. Substitute S is equal to j omega in this characteristic equation. Substitute S is equal to j omega, we get j omega whole cube plus 4 into j omega whole square plus 11 into j omega plus k into j omega plus 9k is equal to 0. So j cube is minus j omega cube. J square value is minus 1 minus 4 omega square plus j 11 omega plus j k omega plus 9k is equal to 0. In this equation, on both sides, equating real parts and imaginary part. So equating on both sides imaginary parts. So we get on LHS side, what is the imaginary part? Minus omega cube plus 11 omega plus k omega is the imaginary part on LHS side. On RHS side, there is no imaginary part, so that is 0. Okay, so that is equal omega square is omega cube is equal and 11 omega plus k omega is the common, omega into 11 plus k. On both sides 1 omega is the cancel, so therefore omega square is equal to 11 plus k. And in this equation on both sides equating real parts. So on LHS side the real part is minus 4 omega square plus 9k is equal to, on RHS side there is no real part, that is 0. So that is equal 9k is equal 4 omega square. 9k is equal 4 omega square. But omega square is equal 11 plus k, and substitute this omega square value into this equation. 9k is equal 4 into 11 plus k, and simplifying, reducing this equation, we get the value of k is equal to 44 divided by 5, so that is 8.8. And substitute this k value into this equation. Substitute k is equal to 8.8 into this equation. Omega square is equal to 11 plus k is equal to 8.8. So we get omega is equal to plus or minus 4.4. And substitute this omega value into S is equal to j omega. So therefore the crossing point on the imaginary axis S is equal to plus or minus, substitute omega value into this equation, S is equal to j omega expression. So we get the crossing point of imaginary axis is S is equal to plus or minus j 4.4. On ordinary graph sheet, mark S is equal to plus j 4.4 and S is equal to minus j 4.4. Okay, and this is S is equal to j 4.4, and this is S is equal to minus j 4.4, and this is the crossing point on the imaginary axis. And now here what is the angle of departure at complex pole A, and this is the complex pole A, and this is complex pole A conjugate. So now here at complex pole A, The angle of departure is minus 16.4 degrees. At pole A conjugate, the angle of departure is plus 16 degrees. So using protractor, measure plus 16.4 degrees at complex pole A conjugate 16.4 and 10, 5, 16. And reverse this protractor at complex pole A using protractor, measure minus 16 degrees, and this is minus 16 degrees, and using scale okay. So this is the angle of departure at pole A conjugate. And this is the angle of departure at pole A. And this is pole A, and this is pole A conjugate, and this is 16.4 degrees, and in reverse direction this is minus 16.4 degrees. Angle of departure at pole A and angle of departure at pole A conjugate, and this is the crossing point on the imaginary axis. S is equal to plus or minus j 4.4 is the crossing point on the imaginary axis, and using this angle of departure and crossing point on the imaginary axis, draw a smooth curve. So this is the root locus of given open loop transfer function. So this is the procedure we can determine root locus.